Welcome to the organic chemistry section of our practice MCAT questions. In this video, we're going to be going through questions 11 to 15. So first I'll show you the question so you guys can attempt it on your own, and then we'll go through it together. So here's question 11, question 12, question 13, question 14, and question 15. Now let's go through the questions together. So in question 11, it says in each molecule below, a carbocation is formed when the alcohol group is removed. Which of the following best describes the stabilities of the carbocations? So the main thing is we have two alcohols, and then we're going to be forming a carbocation from them. And a carbocation is when an alcohol leaves as a leaving group, and then as a result, we get a carbon which has 3 bonds instead of the 4 that it wants, so it's going to have a positive charge. So for both of these molecules, we have a resulting positive charge on the carbon. And then the thing that you need to know with carbocations is that the more substituted they are, the more stable they are. Because when you have a carbocation, you have carbon with a positive charge, meaning it doesn't have as much electron density as it would like, and so it's going to start pulling electron density from its neighbors, so whatever it's bonded to. And if you have more carbons bonded to it, it has more of a source for this electron density than if it's just bonded to hydrogens, which is something that doesn't have a lot of electrons to pull from. So the alcohol on the left, it's bonded to 2 other carbons, that carbocation one. That carbocation carbon is bonded to 2 other carbons, so it's a secondary carbocation, whereas this one on the right is bonded to just 1 other carbon, which makes it a primary carbocation. So between these two, the one on the left has more of a source to draw electron density, so it doesn't feel the effect of its positive charge as much. So therefore, this one is more stable. Alcohol A is more stable. That's something that we can say. And then the reason that it is stable is not due to anything with the resonance. So resonance is just shifting around of electrons. There is a lot of resonance going on between these aromatic rings. And then we can also say there's resonance going on throughout this entire system. So this part is also conjugated, the part that's connecting the 2 aromatic rings, but that doesn't really come to where the carbocation is, and it doesn't really affect it. So that is relevant because some of the options do discuss resonance, but the resonance is not really relevant for why the carbocations are stable. It's more so the inductive effect and how much electron density these carbocations can pull from their neighbors. So option A is saying the carbocation of alcohol A is more stable than that of B since it is non-resonance stabilized. And that is correct. It's more stable, that is what we're looking for, and it's due to something non-resonance related, and it's stabilized by some other factor. So that is correct. That is the most correct answer of the options that were given. Let's look at the other options. B is saying the carbocation of A is less stable than that of B, of alcohol B, since it is resonance destabilized. That's incorrect. So first of all, A is not less stable than that of alcohol B. That's incorrect. And then also it's saying it's destabilized somehow by resonance. The resonance system is not really affecting the stability of the carbocation. C, the carbocation of alcohol B is more stable than the carbocation of alcohol A since it is a resonance stabilized primary carbocation. So once again, incorrect, because it's saying B is more stable than A. That part is incorrect. And then it's saying that A is a resonance stabilized primary carbocation. That's incorrect. So first of all, A is not a primary carbocation, it's a secondary one. B is the one that's a primary carbocation. And then there might be some stabilization due to resonance, because when you have a conjugated system going on, that means that you do have a lot of electron density and all of these different electrons shifting around, so maybe they can contribute some stability to that positive charge. But more so than resonance being the main factor, it's the inductive effect which is pulling the electron density towards this positive charge. So there's a lot of things wrong with C. And then D is saying, and also C, once just going back to that one, C is saying that alcohol A is resonance stabilized, but like whatever resonance stabilization alcohol A is feeling, B is also getting that same stabilization, because that left part of the molecule with the conjugated system, that's the same in both alcohols. So that wouldn't be a difference between the two. And then finally, let's look at option D. It's saying the carbocation of alcohol B is less stable than that of A. That part's correct. But it's saying since it is a resonance stabilized primary carbocation. So that last part is incorrect. It is a primary carbocation, that part's fine, but they're saying it's because it's resonance stabilized, implying that resonance is the reason that A is more stable, or yeah, implying that alcohol A is more stable, less stable, and since, yeah, okay, this one is implying that the alcohol of B, the carbocation of alcohol B, is a primary carbocation, that's fine, but they're saying that it is a resonance stabilized carbocation. And going back to what we said in C, if there is resonance stabilization, if the resonance is really donating some electron density into either alcohol, it's doing it to both. And once again, it's not really because it's a resonance stabilized primary carbocation, it's just the inductive effect. So because the other ones are talking about either the wrong alcohol being more stable, or they're talking about something with resonance, those options are not as correct as A. And A is saying it's because of some non-resonance stabilization force. So that is why A is the best answer. In question 12, it says infrared spectroscopy is performed for a molecule and a broad peak is noted at around 3,300 centimeters. So which of the following functional groups would be expected within this molecule? So we have IR spectroscopy, right? We know that we have a broad peak at 3,300, and then we're asked which functional group is it. So for this, you need to know the different regions for IR spec that are required for memorization on the MCAT, and you should know that aromatic peaks, they kind of show up in a bunch of different places. So some of them, like the CH peaks, they are a bit to the left of 3,000, but there are other peaks such as the carbon-carbon peaks that might be closer to like 1,600, 1,500. You see like a diverse range of peaks for something that's aromatic. So just telling us that we have like one broad peak at 3,300 does not indicate that we have something that's aromatic. Aromatic is more of a spectrum of different peaks that we see. And then an aldehyde, option C, that's incorrect. That would be around 1,700. So you should know that that number correlates with carbonyls. And then we have to choose between B and D. Both of these, they do show up around 3,300. So that part matches up with both of these functional groups. And then the key difference here is in the question, we're told that we have a broad peak. So if we have a broad peak, that means that we have a hydroxyl group because of all of this like hydrogen bonding exchange that's happening. Whereas for amines, we get more of a sharp peak. So the main difference between amines and hydroxyls you should know is sharp peak, I have an amine, broader peak, so sharp peak would look like that, but a broad peak looks more of like a circle than a point. That correlates to a hydroxyl group. So just make sure you keep that part about the peaks in mind as well when you're thinking about functional groups, not just where they are, but whether it's like a sharp or a broad peak. And if you know that, then you know that D is the correct answer for question 12. In question 13, we're asked what modification could be made to increase the volatility of a fatty acid. So we want to increase how volatile a fatty acid is. And a fatty acid, the structure for it will be like a long chain, and then it's a carboxylic acid. So it's a fatty acid raised to carboxylic acid. And we want to increase how volatile it is, which means we want to decrease its boiling point. So what can we do to make something have a lower boiling point than relative to the original fatty acid? Well, we know that fatty acids have a high boiling point. One, because of the fatty acid chain, so the long carbon chain, that can pack together with the chains of other fatty acids because of the hydrophobic effect, and this close packing between the long chains leads to a lot of van der Waals forces, and these intermolecular forces must be broken to convert something from the liquid phase to the gas phase, so to boil it. So that leads to a high boiling point. And then additionally, the carboxylic acid part on the right side of the fatty acid, that has first of all, a dipole, which leads to dipole-dipole forces, and then this hydrogen over here gives us hydrogen bonding capacity as well. So these three main bonds, intermolecular forces or bonds that can occur between the molecules in a solution of this fatty acid, lead to its high boiling point. So what we want to do is either decrease the length of the fatty acid chain so we have fewer van der Waals forces, or maybe get rid of this carbonyl, or turn the carbonyl into a different type of carbonyl so that it no longer has an OH and then it can no longer do hydrogen bonding. So we're looking for something like that. Option A is saying place it in a high pH solution. That probably wouldn't be that effective, because what that would essentially do is just give the oxygen a negative charge, and now you've created a charged solution. Say you put something like NaOH inside, so we have a high pH solution, means it's a basic solution. If we put NaOH inside, now we have this ionic bond occurring between O- and Na+. And you should know that ionic bonds are very strong because of these electrostatic forces between the negative charge and the positive charge. So because of the electrostatic forces, this is a very strong intermolecular force, and you should know that ionic species such as salt or anything that has charges has a pretty high boiling point. That's just a characteristic of an ionic compound, and therefore we can say that this option would not be good. So if anything, it might make the bonds stronger because we have the introduction of charges now. B is saying convert it to an ester. Yeah, that would be good. If we went from a carboxylic acid to an ester, some OR group, now this R group is different from the H group, and since that hydrogen is gone, we no longer have the capacity to hydrogen bond. So now all we have are the van der Waals forces and the dipole-dipole interactions, but we got rid of one of the key things that was making the fatty acid initially have its high boiling point, which is the hydrogen bonding network. We got rid of one of the three main intermolecular forces. So yeah, this would decrease the boiling point of the compound, and then therefore it will increase the volatility, which is exactly what we're looking for in the question. So converting it to an ester, yes, this could reasonably, we can make an assumption that this would lower the boiling point. C is saying lengthening the hydrophobic tail. No, that's incorrect. If you make that chain even longer, then you're going to have more van der Waals forces, and that's going to lead to a higher boiling point instead of a lower one. And then option D is saying if we decrease the temperature of the solution. Of course not. If we decrease the temperature of something, we're going further away from the boiling point. You need to increase the temperature of something, and then that brings it closer to its boiling point, and it increases like the vapor pressure above the liquid. That would lead to an increased volatile solution. So you want to increase the temperature, not decrease it. Therefore, option D is correct. And then B is the best answer for question 13. In question 14, we're asked which of the following amino acids does not rotate plane polarized light. So we're talking about something rotating plane polarized light. Which one does not? To rotate plane polarized light, you need to have a carbon which is chiral, meaning that there is no plane of symmetry inside the carbon. So if a carbon doesn't have a plane of symmetry, it's chiral, it can rotate plane polarized light, and usually what we're looking for is a carbon which has 4 different groups bonded to it. So you should know with amino acids, they have their general structure. They have a carboxylic acid, so they have a middle carbon, a carboxylic acid, an amine group, so positively charged, a hydrogen, and then an R group. And then if these 4 things are different, then the amino acid is chiral. But if the R group is the same as any one of the other things, then it's not chiral. And then you should immediately know that in glycine, we have an R group, which is hydrogen. Since it has 2 hydrogens now on this central carbon, the molecule is no longer chiral. Therefore, it does not rotate plane polarized light. So our answer for this is glycine, and you should already have this as a very common fact inside your brain. Just along with everything else you've learned for amino acids, you should know that glycine, one of its key characteristics is that it does not rotate plane polarized light because it is not chiral. So let's look at our groups for the options that we had. Valine, it'll be down here in the hydrophobic part. So it has this group, which is different from everything else on the chiral carbon. Next we had glycine, threonine, and tryptophan. So where are these? Threonine is over here. Here's its R group, so it's something other than hydrogen. Tryptophan over here, definitely a different R group than just having a hydrogen. And then just glycine now. Glycine is over here. Its R group is not shown, but that's because the R group is a hydrogen itself. So because glycine has two bonds to the same atom in the central alpha carbon, it is not a chiral carbon, and then it does not rotate plane polarized light, whereas all of the other ones have 4 different groups attached to that alpha carbon in the middle, and then the alpha carbon is chiral, so they can all rotate plane polarized light. In question 15, we're asked which of the following pairs of monosaccharides are anomers. So an anomer is when you have 2 different anomeric forms of a sugar, and how that exists is when the sugar is closed up in its ring form, then the OH at the carbon 1 position, the anomer carbon, it can either be going up in the Hawthorne projection like this, which would make it a beta anomer, or at that position it can be going down, and then we have the alpha anomer. So at carbon 1 of the Hawthorne projection, depending on whether it's going up or down, that overall sugar is called either the alpha anomer or the beta anomer. And then anomers can interchange between each other because the ring form can open up again into the linear form, and then the sugar can come and close again and then shift between the alpha and the beta forms of the same sugar. So anomers are when we have the same sugar, but just the way that the ring closed, the attack that happened to close the ring came from either the top phase or the bottom phase. So for a pair of anomers, we need 2 sugars that are the same sugar, and then one is the alpha form, one is the beta form. So option A is incorrect, because first of all, we have the beta form of each instead of alpha form and a beta form, and then we have 2 different sugars. The first one is glucopyranose, but then after we're talking about mannopyranose. So glucose and mannose, those are 2 different sugars. For something to be an anomer, it needs to be the same sugar. B is also incorrect because of the fact that we have, once again, gluco and mano, so different sugars, even though we do have this alpha and beta part down correct, so that part is fine. And then C seems correct, yeah, because we have beta, the beta form of this sugar, glucopyranose, and also the alpha form of the same sugar. So that means that we're talking about glucopyranose and the different Hawthorne projections that we can get. So glucose, it can open up to its linear form and then close to form the beta form, and then that same sugar can open up, close, and have an attack from the other side to give us the alpha form. Yeah, those are 2 anomers. D is incorrect because although we are talking about glucopyranose in both, first of all, we don't have the beta and alpha forms, and second of all, we have the D form and then the L form. So the D and L refers to the overall orientation of like the hydrogens and the OHs, where they are, meaning that on the chiral carbons on this sugar, they're in opposite directions. So these 2 would be enantiomers of each other. The D form of a sugar and the L form are enantiomers, but that's something different than what we're talking about. We're talking about anomers, and you should know anomers, they're not enantiomers, they're not diastereomers, they're a different type of isomer between 2 compounds, and that's compounds that differ only at the anomeric carbon, and then they can convert into each other by just opening the ring and then closing it again. We don't have to like break a certain bond and then remove that thing and then bring another bond in. We don't have to like break and create new bonds as we do in enantiomers that are like much stronger covalent bonds. Here we're breaking like a weaker bond which can just open and close again in an equilibrium in a ring closing formation. So therefore C is the only correct answer for giving us a pair of anomers. That's it for the questions in this video. If you like what you saw in this video, make sure to check out our course on teachable.com, our whole 30-day MCAT prep course. In that course, we have a lot of different lessons where we go through the topics that we're talking about, like organic chemistry, biology. So we also explain all of these topics in as much depth as you need to know for the MCAT. And then we also have, just like this video, a lot of questions, which we go through what the question is asking you, as well as the correct answer and the explanation for why the other answers are incorrect. So if you like what you saw here, check the description to see how our course is, and we have a few different packages available, so find whichever one works for you. And that's it for this video. I'll see you guys in the next one.